Alright, good morning. What we're going to do is we're going to do the Nature of Science notes. I'm going to try and record these for those of you that are gone. A bunch of you are gone for athletics. And a few people stayed home because of the heat. So, here we go. Follow along. These should be going on page 12 to page 15. I'll try and be specific about which page we're on. So we're going to start on page 12, and we're going to talk about the nature of science. So at the top of page 12, go ahead and list nature of science. Now this reading can be found in that introductory chapter and the Nature of Science chapter in your textbook, which you can access on Schoology. Remember, the password and the username are in the front inside cover of your notebooks. Okay, so I'm just going to hit some highlights, hit the bullets here. We will see these frequently for the rest of your science education. Alright, so the first thing about Nature of Science is that humans they do it, okay? We have this ability to make observations and inferences. We just do this automatically. You probably do it without even thinking about it. It's just part of our innate ability as humans. We use tools to take measurements. It could be anything from a ruler or a stopwatch to something complicated like a MRI machine where you're looking at distribution of subatomic particles. If we smash two protons together, we get all this data. It's a very expensive, very specific tool, but it could be anything really. It's collaborative. Meaning, very rarely does one person make an invention or a progressive step in science, like the mad scientist that you think about in maybe like Flubber or Mary Shelley's Frankenstein, something like that. It's very rarely is it an individual effort. Many of the Nobel Prizes have multiple recipients of the award for a single project. Science builds on itself. There are some really good examples. You've probably looked at the progress of an atom. We once thought, back in 400 BC, Democritus said an atom was the smallest thing that could be divided. And if you fast forward to current thinking, we think we have things like dark matter and regular matter, and there's about 46 subatomic particles that make up an atom. So things smaller than protons and neutrons and electrons. And so science has continuously built on itself in the areas of atom understanding of what is an atom. We see the same thing with the solar system model. Going from a geocentric or an Earth-centered solar system model to a heliocentric or a sun-centered model was it kind of a shift in thinking about the time of the Age of Enlightenment, where astronomy really became one of the first sciences. And then, of course, from there we got physics and we started looking at chemistry, and kind of all stemmed off from that. But yeah, science builds on itself. It's very rarely done by one person. Science, the distinction between science and pseudoscience or fake science is that science can make predictions. Okay. If science is not producing a theory that you can use, then it's not really useful, and we kind of it's kind of cool, it's interesting, but we tend to think of that more as art versus science. And so science really will make predictions, testable predictions about space, about the nature of things, about what's underneath our feet, etc., etc. So these predictions are used to solve problems. So when we say, well, why do we care about science? Well, they try to solve societal problems, these big ticket items. I'm not talking about like, I need a pair of shoes, I lost my shoes, I'm trying to solve this problem. We're talking about, how do I feed 100 million people? You know, if my primary source of food is rice, and I'm over in the Asian countries, there's a specific country next to India, they grow rice and they flood every year. The ocean comes in and destroys their crops every single year. And the thing about the ocean, it's got salt in it. And so once you have salt in your fields, those fields are no longer good. This is a very dense population of people, and they survive on rice. Well, if you need to solve this problem, you're going to use science, all these tenets of science, and you're going to try to create a strain of rice that can survive in salt water, which is kind of a unique thing for plants. Plants don't typically like salt water. They like fresh water with minerals, but not a lot of sodium chloride that comes out of the ocean. And so that's a problem, and we've used science to genetically modify that rice strain so that it can grow during the monsoon season when their fields all get flooded with salt water. And so that's an example of how we use science to solve problems. Well, what we're going to do right now, I'm going to erase this. We're going to take a pause in the video, and we're going to go into the scientific method and what is the 7E model. So go ahead and go to page 13 in your notebook. All right, you should be on page 13 now. We're going to talk about the scientific method and the 7E model. So the scientific method and 7E model should be written at the top of page 13 in your notebook. Now, there's a lot of different ways to write the scientific method. I've chosen this one that I use quite frequently. So go ahead and jot these down if you haven't already, but we have observation, question, hypothesis, experiment, collect data, analyze, and write a conclusion. This is, roughly speaking, the scientific method. There's different ways to group this, different ways to attack it. Some people write this linearly, some people write this like in a circle, like a flow chart. But essentially, you're looking at something, you're noticing there's an issue, you come up with an idea about how to solve that issue, you try it, and then you look at your results and see if you did a good job or not. And then you may need to adjust your hypothesis, or you have the answer, you've solved your problem, and you write a conclusion. And so this is fairly commonplace. You've probably seen this before. The textbook that we use follows what's called a 7E model. And so I'm going to kind of group the scientific method that you're familiar with into the 7E model. Okay, so this is roughly grouped. This is my own kind of work. I'm very familiar with this, and so as I was reading through the 7E model in the textbook, I came up with this grouping. And so really, when they elicit, this is what do you see, the think about it sections, you're trying to kind of get your interest peaked here with the elicit and the engagement. It's kind of almost the same thing a little bit. This is really this piece right here about observations, making up a question, or seeing a problem, and then coming up with an idea. You're starting to think about it, right? You're really thinking about the problem of what's going on. This is eliciting some relevancies, and you're engaging with the discussion about what's going on. And you'll see these sections in the textbook, and they call them "What do you see?" and the "Think about it" section. And then we come down here to the experimentation, collect data, analyze, interpret. And I've got this little cyclical symbol here, meaning if your experiment doesn't work, right? If you experiment, you collect data, and you realize you need more data, well, you can go back to your experiment and do it again, or change it and collect different data, and then analyze, interpret. Oh, I still need more. I'm going to change my experiment. I'm going to collect different data. And you can kind of go back and forth over and over and over. And so that's really called exploring, right? You're investigating. We're going to do some investigations in here. And then you're explaining what that investigation just showed. And we want to use academic language. We want to use the geo words. And you'll find the geo words listed at the bottom of your objective tracker, and they're off to the side in the textbook. And so we'll go through that when we get to that point. You want to elaborate, and these are the digging deeper or the think about it again sections. There's some checking up questions. Did you get it? The understanding, the application questions. So the textbook really uses these explain and elaborate parts of the 7E model to get you to analyze and interpret data that came from experimentation, came from this investigation. And once we have this data, we kind of mull it over in our heads. We collaborate, because that's the nature of science, and we use tools, and we try and make predictions. We try and make rules, going back to the nature of science. And so the 7E model includes explore, explain, elaborate, which we'll go through frequently, and sometimes back and forth a little bit in the textbook. And then at the end of the day, you will have a quiz. And so there's a 5-question quiz at the end of each section we'll be doing. This is the ones that 70% of your grade. We'll be able to redo those, etc., etc. But this is the evaluate section, where it's a, did you get it? Did you understand what you were supposed to understand? Okay. And at the end of the day, we call these formative assessments, meaning that, you know, they're used for me to see if I did a good job teaching, and they're used for you to see if you understood what you were supposed to understand. And if you didn't, you know, there's a reteaching section and a retrying section available. Okay. The extend, in the textbook, this is called the inquiring further. We may or may not get to the extend section. These are kind of like the fun, nice to have things. And if we get bogged down with these investigations and the vocabulary words, and we're stuck, it's a difficult concept, you just don't move forward very quickly, then we won't be able to get to the extend section. But if you kind of, oh, I know this, we learned this in 8th grade, and we kind of blaze through this, and the evaluation says, well, man, everybody knows it, so it's duh, okay, then we will have time to do the extension. We'll kind of play that by ear, okay. So this is the scientific method on the left-hand side here, and it roughly translates into what's called the 7E model that your textbook uses. And so you'll look out for these. What do you see? Think about it, investigate, digging deeper, geo words, think about it again, checking up, understanding, applying, the quiz, and then inquiring further sections in the textbook. Okay. All right, we're going to turn to page 14 here. Okay, we should be on page 14. If you haven't already, go ahead and copy this down. You can always pause the video when you need to. But this is the engineering design cycle, and it consists of this loop where you have a goal that's derived from your problem, okay, that you observed, and it's got inputs. And so you look at what all is involved in that problem, or what is all involved in solving that problem, okay, getting your steps down, getting to that goal. And so it takes a process. This is the scientific method, or the 7E model process, and it kicks out an output. And so this is your results or your conclusion, or at the end of your day you evaluate and see what you got, right? And your feedback is whether or not you answered the question. And so sometimes you may have answered the question fully and completely and you're done. Sometimes you answer the question partially and it's about a 90% solution, and that might be good enough. Or you might have answered the question like you have half the answer, you have 50% of the solution, and it's not good enough. And so you reevaluate your goal and you try and see if there was any additional inputs that you missed, and then you put it back into the process of testing it, evaluating it, and then you see what you get, and then now maybe you have that 90% solution and you're good, and that's good enough. Okay, so these criteria are set in your goal, and sometimes these could be called SMART goals, where they're specific, they're measurable, they're attainable, it's got inputs and steps to get to that goal, things that come along that you may not have anticipated that become problems as you try and solve it, and that's why it's a cyclical design cycle. So when you engineer something, you're using the scientific method or the 7E model in a practical sense. You're trying to get somewhere, you're trying to make something or solve something, and we as humans just do science naturally. It's just what we do. If you ever want to get better at something or make something, you follow this engineering design cycle in your head, and it may be very quickly, it may be long and drawn out, not a piece of paper with lots of people, or it just may be a quick thought process in your mind. But we do use this. And so there is a table that you can find in your textbook. I'm going to kind of go ahead and detail out some of the bullets right now. So when you look at your goal, you want to define the problem, you want to identify the resources that you have, you want to identify any possible solutions. You may have already done this, right? If you know the problem and it's a well-defined problem, I don't have a pencil, and you have a solution that you've already used and it works, I go to the back of the room and I get a pencil. Well, done, right? But you have kind of thought through that in a meaningful way, right? Sometimes there's constraints. Maybe you don't have a pencil, your problem, and you identify a solution that you previously used, like, well, I'll just go to the back room and get a pencil. But one of the constraints is that you can't leave your seat. Or if you identify your resources, maybe all of the pencils are gone from the bucket in the back of the room. Okay, so now we have a more meaningful problem. So, well, okay, I have a problem. I've looked at previous solutions. My resources are a little bit less than they usually are, and I have a couple constraints put on me, right? Or maybe I have a boot on my foot, and I can't move around very hard, right? Or very easy. So that's kind of the goal. Inputs. So the inputs here, you're going to complete an investigation. Now, you don't really understand the problem completely unless you try it, right? You have to investigate. You have to look and see what's available. And that this investigation, once this is complete, once you've learned some new academic language or some new vocabulary, those inputs get added to the original problem, because every situation is going to be different. Okay, the process, right? You're going to evaluate your work. You're going to examine trade-offs. In the Marine Corps, we call this COA development. So a COA is a course of action. There's lots of different courses of action, and you get to 70% solutions and 20% solutions and 90% solutions, and these different ways to do the problem or solve the problem. It's called COA development, so the course of action. What are we actually going to do, right? You're going to design experiments, you're going to build models, you're going to compare and contrast these COAs, or the trade-offs, if you will, of doing it one way versus doing it another way. One way it might be fast and easy, but it might be really expensive, right? Or maybe it's cheap. Maybe you want to put a pool in your backyard. Go grab a shovel and start digging. You'll get there. It'll be really hard. It's really cheap. Take you a long time. Might not be worth it, right? And so you got different COAs. Maybe you go rent a backhoe and you do it yourself, right? A little bit more expensive, but not super expensive. Or maybe you just sit down in a lawn chair with some iced tea and you watch somebody put your pool in. Okay, a very expensive way to do it, but it's much easier, much faster. And so these COAs are all built into this compare and contrast on possible solutions. We test to see which one we really like. We use a scientific method, and at the end of the day, we're going to get some outputs. So your outputs, it could be an intermediate step, meaning you might not have gotten to the full solution, maybe you just got part way there. The presentation, maybe you're completely done, you're buttoning it up, you have a product to show somebody if you're selling something, or presenting it to a journal or a colleague or something like that, or a friend. Your results, okay, this is what you get from the process. Okay, so your feedback, really important that you always get feedback on your outputs. Okay, if your output was an intermediate step, your feedback might be something simple like, hey, this is the right direction, you're in the right realm, we're not quite there, I'd like to see this instead of that, something like that. If you're done, your product is made, maybe you get, hey, that's exactly what we wanted. Okay, maybe it's something else. So feedback is an important piece of this loop, and you'll put it right back into the new problem. So maybe with feedback, your problem got tweaked a little bit, and you just go back through the process, and that's why it's cyclical. Hi, well, end of class today. I'm buttoning up this video, just doing some quick editing, and I'll put this on YouTube and then link it to Schoology for you, so hopefully you're viewing it here. But I had a good day in class today, some hard notes, pages 12, 13, and 14, some typical handwritten notes, how we like to do them in class. And tomorrow we will be doing tables and graphs, and so come ready to get those done. And then next week we'll be starting our first objective in the earth science curriculum. So this week's all been about setting it up, how do we do school, working with our notebooks, and what science is. And then next week we'll really get into the meat and potatoes of class. All right, hang in there, and if you have any questions, of course, shoot me an email. Communication is always the best way to go, and I'll talk to you later. Thanks.